Welcome everyone to this Thursday's PCS seminar here in Daejeon at IBS. It is a great pleasure that we have today with us Professor Jayson Cosme, and I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Yes, hello, good morning, good afternoon to everyone, wherever you are. So it's a great pleasure to introduce Jayson Cosme, in particular because we were working together at Massey University in Auckland some time ago. So let me therefore jump immediately into the CV of Jayson. So Jayson had his Master of Science obtained from the University of the Philippines. And then he moved to make a PhD with Joachim Brandt, who was one of my colleagues back at the time in New Zealand, in Auckland. And then he finished this, Jayson finished this PhD successfully in 2017 and moved for a postdoctoral position to the University of Hamburg, to the Center for Optical Quantum Technologies, or the Institut für Laserphysik. And just those of you who remember the recent presentation by Peter Schmeicher, this is exactly the same place, where also Jayson has been working on as a postdoctoral scientist. And then since 2020, he accepted a professor position at the National Institute of Physics at the University of the Philippines, where he is now connected to with us. And Jayson has had a number of very interesting research results and publications. And in particular, he is now also since some time very active in the field of Fourier physics, if I may call it so, and time crystals and other things. And this is the reason why we have him today with us. So Jayson, the floor is yours. Please go ahead.
Yeah, thank you, Sergey, for the kind introduction and for the invitation. It's a real pleasure to share with you the work that we have been doing for the last 3 years about dynamical control of phases and time crystals in an atom-photon system. Specifically, it's a cavity QED system that I will describe later. And I had a wonderful time collaborating with the following people shown here. I'm a theorist myself. I'm a part of the theory team together with PhD student Jim Schulte and Professor Ludwig Mathai. And we're really fortunate to be closely collaborating with essentially next door neighbors who are experimentalists from the group of Professor Andreas Amerik. Hans Kessler is a wonderful, talented postdoc in his group. And Popla Konkambut, Christoph Georges are Andreas's PhD students. Okay, so over the last couple of years, we are mostly interested in this rather fundamental question of what happens when we shake a many-body system. And technically speaking, what we mean here by shake is what happens if we change one of the system parameters periodically in time. And there's this very nice, simple example in classical physics, which some of you, or if not most of you, may already know, which is this Kapitza stabilization of the inverted position of a pendulum. So we know how this upside down position of the pendulum is a highly unstable equilibrium position, right? So if you just nudge on it a bit, it will go back to the equilibrium position, which is the pendulum bob pointing downwards. So that's not so surprising. The interesting thing here is if you somehow shake the pivot point, and if you shake it fast enough, you can stabilize that inverted position, which is a very fascinating effect, I would say. So this phenomenon can be understood by essentially describing the equations of motion using a separation of slow and fast variables. So what you can do is you basically integrate out or time average out the fast variables, and this will lead to an effective potential for the slow variable, which is given by this form here. I hope you can see my cursor. I'm kind of assuming that you can see my cursor. Okay, good. And if you plot this effective potential as a function of theta being the angle the pendulum makes with respect to the vertical position, you see that you have this shape here, which looks like a bell curve. But the important point here is the position when theta is equal to pi, meaning it's upside down position, it is a maxima. So that means if you just push that thing a bit, you will eventually roll down the energy hill and go back to theta equals 0 or theta equals 2 pi, which is this equilibrium position, right? But what essentially happens if you shake the pivot point at some critical frequency, if you shake it fast enough, you eventually get this local minima. And this causes the stabilization at this upright or upside down position, right? So that's nice and cool. But what we're interested in with many body system, with periodically driven many body system, and in particular, we are interested in systems that host competing phases. So, for example, if you look at the steady state phase diagram of a given system, you can have 2 or more competing phases. So you can imagine this to be a phase diagram of some arbitrary physical system. On one axis, you have one parameter, on the other axis, you have another parameter, right? And what we found out, but really not just us, but also other people working in this very active field of flow K driving and flow K engineering, if you like, is that by periodic driving, you get 2 possibilities that I will kind of describe later more in detail. One is the possibility of renormalizing the phase boundary. So say, for example, you are in your phase diagram, let's say somewhere here, where in equilibrium or steady state, without any periodic driving, you expect to see phase C. But with periodic driving, you instead get phase A, right? So in this sense, you are renormalizing, you are kind of changing the shape of the phase boundary between different phases in your system. So that's one possible result or effect of periodic driving. And another is the emergence of genuine dynamical phase, which has no counterpart in equilibrium. So you can have this new phase emerging called phase D, and that's interesting by itself. So these are 2 possibilities that you can have when you periodically drive a many-body system. Okay, so just to give a few examples. So what do we mean by renormalization of phase boundary? There's this one concrete example was discovered by Andrea Cavalieri and his group almost a decade ago, where they look at this high temperature superconducting material called LESCO. And this is more or less the phase diagram of LESCO. On one axis, you have temperature, and the other axis, you have doping. And they have LESCO at this suboptimal doping and at some temperature above TC. So you don't expect to see superconductivity in equilibrium. What they did was they shone light, so they shine light on the sample, and to their surprise, they were able to see superconducting response. Although this just transient superconducting response, I have to say, which is kind of cool by itself, right? That somehow in equilibrium you don't have any superconductor, but by photo excitation you're able to get a superconducting response. So that was almost a decade ago, and the field remained active. And just recently, last year, they look at this another high TC material called YBCO, as depicted here, and they clearly show that by shining light, doing a pump probe type scheme on this sample, you can go from non-superconducting without driving, and then with driving, you get this, for example, 1/omega divergence in the imaginary part of the conductivity that you expect to see for a superconductor. So those are just 2 examples of how you can renormalize the phase boundary. And as for the other possibility, which is the emergence of a dynamical phase or a non-equilibrium order, just recent things going on with time crystals, as you can see here. So basically, I mean, in a nutshell, time crystals are, they are analogous to solid state crystals. We know that solid state crystals break continuous space translation symmetry as the atoms localize in space, right? Time crystals, on the other hand, specifically discrete time crystals, they break discrete time translation symmetry. So what do we mean by this? Well, if you have a system, you periodically drive it at some period t, the system reacts at the multiple of the driving period. So it acts it results to a subharmonic motion in your system. And this has been nicely shown in this experiment using ion chain from Chris Monroe's group, where when they switch on interaction, long-range interaction between the spins, they were able to see this robust period doubling response. Okay, and although I have to say here, I also have to mention, I think it's an important ingredient of this type of time crystals is this disorder. So some of you may be familiar with the idea of many-body localization, that a sufficiently strong on-site disorder can drive the system into a many-body localized state. And the purpose of this here is to basically prevent the heating of the system, which brings me to my next point, that ultimately the challenge in periodically driven many-body system is the problem of heating. So we know that in a generic non-integrable system, periodic driving will eventually lead to heating, right? And there are possible workarounds. So one, you can just accept your fate, the fact that, okay, the system will heat up, but if I get something non-trivial in the meantime, if I get some kind of non-trivial pre-thermal state, maybe I can probe the system fast enough before the heating sets in. So I can do all sorts of operation and to maybe make it functional during the time scale in which you don't relax to a featureless thermal state, right? So that's one possibility. And then the other is to make the system integrable or non-ergodic. And then, as I've said in the previous slide, you can do this, say, for example, by using many-body localization. You prevent the system from heating up. And then last but not least, you can introduce dissipation to the system. And what this will do is it will provide the cold bath for your system that will essentially take energy out out of the driving, out of the energy that you are inputting into the system because of the drive. And the focus of this talk will be on this, which is periodically driven dissipative system. Okay. So in particular, the system that we are interested in is this cavity QED platform, as depicted here, where you have a Bose-Einstein condensate. I can see that there must be a question.
Yes, Alexei,
Yes.
please.
Yeah, could you please go back to the previous slide? I wonder, is there also a fourth route, like fine-tuning? You could perhaps fine-tune a system in a way that it doesn't heat up, or would that make it integrable in some sense?
You can do that. So as a matter of fact, it turns out that you can actually slow down heating simply by increasing the driving frequency. So if you tune away from the relevant resonances or energy frequency in your system, you can do that.
Yeah, that's nice to know, but that's not exact. I mean, I meant, can you fine-tune your system in such a way that it's not integrable, or at least not integrable in common sense? There's no dissipation, and yet it doesn't heat.
I
mean, what you were describing here, it applies to generic systems, but I wonder whether you can do fine-tuning that might even be fragile. That is, once you deviate even slightly, might take a long time, but the system would heat up. But I'm curious whether it's possible to fine-tune in a way to kill the heat.
I mean, in isolated systems, there's this kind of emerging field, this notion of quantum many-body scars, where you basically choose, it's a fine-tuned initial state where you only explore a certain part of your phase space, right? And I think I'm not sure if there's already enough research going on how this extends to periodically driven system. If it is possible to find scar states, if you like, in periodically driven systems, I'm not sure. But in isolated systems, you can do that. You can choose a particular initial state that will not thermalize. The question is whether this also applies to periodically driven system. And my answer is I don't know.
Okay, thank you.
Okay. Great. So yeah, so this is the system that we are interested in. It's an atom cavity system. So as I've said, you have a BEC inside the single mode optical cavity. So you have this optical resonator. They're highly reflecting. So if there's a photon that happens to get scattered into the cavity, it will undergo multiple round trips. In fact, 100,000 round trips typically before it eventually escapes, right? So it's an open quantum system. There are photons leaking out of the cavity at the rate given by kappa. Okay, so what we're doing is that we are pumping photons from the side. So this is the cavity axis, and this is the transverse direction. So in the transverse direction, we are shining a standing wave potential for the atoms by means of this transverse pump laser here. And it is characterized by some wavelength lambda, okay? So typically, as a theorist, what we usually do is that we go to the rotating frame of the pump. So that means everything will be measured with respect to the pump frequency. So for example, the cavity frequency will be measured or will be given by or characterized by this variable delta C, which is the pump cavity detuning frequency. Okay.
Just I'm lost. Not okay. I'm lost. So again, so in the x direction you have what? You have the BC. Is that right?
Well, this is the coordinate system that we're using, right? So in
in the y direction. Okay, in the y direction. So yes, I'm lost in your directions.
Right. So it's a two-dimensional system. So we consider like a two-dimensional BEC. It has a spatial extent both in the y and z direction. Okay. And then the pump, it is aligned across the y direction. So what it does is that it provides a standing wave potential for the BEC.
What about the cavity though? You spoke about the cavity.
Right. So for the cavity, when you start, if a photon gets scattered into the cavity, it will go multiple round trips, and what will do is it will occupy the single mode cavity field, right? And it will also have
the photon is scattered or emitted out of this BEC setup. So
yes, exactly.
I see.
Right. So you can think of the why would we'll do that? I will get to that point later. Yeah, why it will scatter photons into the cavity? That's an interesting point. Yeah, that's a good question.
And the x direction is currently not of relevance.
No, it's not. It's not. At least not on this level. We forget about the x direction. We only look at the minimal kind of dimension where you have the pump and you have the cavity.
Thank you.
Okay. Okay. Yeah. But Sergey made an interesting point. Why would the photons get scattered from the transverse direction from the pump then into the cavity, right? So that's an interesting question that we'll answer in a couple of slides. Okay, but before going to that, first let me try to maybe convince you, at least on a conceptual level, that will be followed by a more rigorous mathematical kind of argument, why an interesting feature of this atom cavity platform is this infinite range cavity mediated interaction. Okay, so the way to think about this is a single atom will effectively shift the frequency by an amount delta naught. Okay. So now if there's a second atom, it will see a different cavity frequency. It will be shifted by amount delta naught. And it doesn't matter how far the two atoms are for as long as they're inside this optical resonator. So now you can imagine a case where having n atoms and you will get an effective light shift given by this, right? So recall that delta C here, this is the effective pump cavity frequency. You can think of it as the cavity frequency, but because we are in the rotating frame of the pump, then you talk about the tuning with respect to the pump frequency. Okay, right. So now, since this is, I think, mostly, if not exclusively, a theory audience, I can maybe get away with showing a bit of mathematical details. So the beauty of all these designer platforms like the cold atoms, etc., is that you get a good handle as for the microscopic details of microscopic processes and parameters in your system. So you can rather straightforwardly write a many-body Hamiltonian that describes your system. And for this atom cavity system, you basically have 4 contributions. So one, you have the cavity Hamiltonian, which is just given by this. So again, delta C is just the cavity frequency. A is your operators corresponding to the photonic degree of freedom, to the cavity photon. So we have a single mode quantized cavity field, right? And you have the atomic Hamiltonian, where you have this usual second quantized form that you have. So psi is just the field operator for your atoms. So the first term here is just the kinetic energy. And the second term is just the optical lattice produced by your pump. So recall that, this is again the coordinate system that we're using. Y is the axis where your pump is aligned. So you have this cosine squared ky potential in there. And you have the intensity of the pump, which could be time dependent, given by alpha p squared. You also have the inherent contact interaction between your atoms, which is of this form, right? So UA tells you about the strength of the contact interaction. And last but not least, you have the atom cavity coupling. So the first term here, is just the optical lattice produced by photons occupying your single mode cavity. So it's along the Z direction. And this is the interesting bit here. So this is it's a checkerboard lattice. It's cosine ky, cosine kz. So it's a pump cavity interference term, if you like. So this is the interference between the pump field and the cavity field. Okay? And what I'm saying here is, because of this term, this effectively introduces a long-range interaction for the atoms. And in order to see this, we have to do a bit more mathematical gymnastics. So you write down the usual Heisenberg operator or Heisenberg equation for your atomic field operator and for the cavity photon operator. So it's given by this. So here, note that we are really kind of emphasizing the fact that we have an open system. You have to take into account dissipation. So you have this kappa term here, which is the rate at which photons are leaking out of the cavity. And to show that that you have a infinite range cavity mediated interaction, it is insightful to go to the so-called bad cavity regime, where kappa is so much larger than all the other energy scale in your system, in particular the recall frequency. So the recall frequency, the way to think about it is it's essentially the energy scale, or the frequency or the time scale of your atomic motion. So in this kind of overdamped regime, what it means is that the photons are moving so fast that essentially, from the point of view of the atoms, they're always kind of relaxed towards they're always relaxed in their steady state, right? So the cavity photons adiabatically follows the slow atoms. So then what you can do is you can adiabatically eliminate your cavity photon dynamics. So you simply set the left-hand side of this equation to 0, right? And then you solve for A. And once you have A, you plug that expression back into the Heisenberg equation for your field, and then you derive an atom-only effective Hamiltonian. And this is what it looks like. So this is the atom-only Hamiltonian that we will get after adiabatically eliminating the cavity photon dynamics. So let's maybe unpack it a bit further. So here, the first line, so this is the atom-only Hamiltonian. So the first line is just the atom Hamiltonian that I showed a couple of slides ago, right? So this consists of the kinetic energy and the pump term, the optical lattice along the y direction. The second line is nothing but the short-range interaction between your atoms. It's the contact interactions between your atoms. And then this last line here is what we got after this substitution, after adiabatic elimination. So you get this non-local interaction potential for your atoms. So you have this cosine potential, right? So this is what we call the long-range interaction. And the strengths of this long-range coupling is given by this. So these are just the parameters that you have in the atom cavity setup. So alpha P is the pump intensity, right? Delta naught is this frequency light shift that you have because of the presence of an atom inside your cavity. And then you have this effective detuning. So this is the collective effect of the atoms, how they shift the cavity frequency. Okay? So note that in general, just energetically, okay, there's a question, I think.
Yes, Juzar, please unmute yourself.
Hey, Jayson, sorry to interrupt you, but just wondering, since you
introduce the effect of copper, which is damping,
Right.
why is your atom Hamiltonian still Hermitian? It looks like a Hermitian Hamiltonian to me, right?
This is also my question. Okay.
Right. It is still Hermitian because let me that's because the atomic part is Hermitian. That's a that's a short answer. So there's no loss term in the atomic sector. So you only have loss term in the cavity sector.
Yeah, but the atomic and the cavity sectors are connected to each other, right?
Right.
So what you get is basically an effective Hamiltonian for the atomic sector, but even though you are introducing damping, it turns out to be a Hermitian Hamiltonian. I mean, this is a bit, because normally what I would think about is if I have damping, either I would come up with a non-Hermitian Hamiltonian, or you would have another dissipation theory altogether, like a master equation or something. So I'm quite confused here why it turns out to be Hermitian eventually.
Right. So I mean, I don't have a ready answer, but we could maybe talk about it offline, since I think it's easier to discuss this if we go into like the nitty-gritty and the details of what the Hamiltonian looks like and see how.
Maybe I guess this happens because as you say, I mean, you replace. There is no damping process which you describe. You just say that the photons are in some kind of ground state or whatever, and then the atoms move in that effective potential. This is similar how you would assume that all your electrons are always in the ground. This is kind of like it sounds almost like an adiabatic approximation.
It is.
Yeah, but then the copper, so in the Heisenberg equation of motion for A that you have, you just have a minus copper term. So if you go to I think the next slide. Sorry, further ahead. Yes, exactly. This is just a I mean, it's minus kappa A. If I was to write an effective Hamiltonian such that, my equation of motion remains as Heisenberg equation of motion, I would immediately see a non-Hermitian Hamiltonian pop up here. So, okay, we can discuss this afterwards, Jayson.
Yeah.
Thank you.
Yeah. But it's an interesting point. But maybe I don't know, maybe it will help explain this or not, but I think it has to do with the way the atoms couple to the photons. And if you look at the atom cavity coupling terms, from the point of view of the atoms, they are still Hermitian. But we can discuss this later. I think it's going to be easier if we simply just go through the details, I think.
There's another question by Jung-Yun. Jung-Yun, please.
Yeah. So can you please go back? Let's write back, please. Yeah. So once you describe the atom cavity interaction, how do you obtain this interaction in the middle? So because usually interaction Hamiltonian is given by a product of linear operators with the field.
I'm sorry, I'm hearing two voices, so that's why I was lost a bit. Sorry.
Sorry, because I'm in a noisy environment.
Okay.
Yeah. So once you describe the atom cavity interaction, so there is some. It seems there is an effective description in the middle. So my question is, how do you obtain this interaction?
So this pump cavity interference, you mean?
Yeah.
I mean, this is just because you basically have. Okay, so well, technically, you obtain this by. You can imagine a single atom to be a two-level system, right? So you have the ground state and the internal excited state. Okay. And what we're essentially doing, so in quantum optics language, is we are driving this transition off-resonantly. So in doing so, we are effectively in the dispersive regime where you can just forget about the excited state and everything is happening in the ground state. Okay. So in theory, what you do is you basically adiabatically eliminate this, and this will create this cross-coupling term given by this cosine ky cosine kz. Physically, what this only means is, okay, you have the standing wave potential along the y direction, and then you have a standing wave potential along the z direction. At some point, they will interfere, and this will create this potential for the atoms. So that's another way of thinking about it. Okay.
Yeah.
I hope that answers the questions. Okay. Right. So as I was saying, so I think we this is the last slide that we were into. So you can basically change the sign of this effective long range coupling strength, right? Just by simply changing the cavity frequency. If it turns out that delta effective, this is effective cavity detuning, is negative, so V will be negative, then energetically speaking, your kinetic energy in your short range interaction, they increase the energy of the system, but you can effectively reduce the energy by scattering photons into the cavity. So if you activate this cavity-induced long-range interaction, meaning you start scattering photons into the cavity, then you can lower the energy of the system, right? So what this means is the following. So we expect that at some critical pump strength, it becomes energetically favorable for the system, for the atoms in particular, to self-organize in order to scatter photons from the pump direction to the cavity direction. And they will only able to do so if they somehow arrange into this checkerboard pattern, right? Because this is the arrangement in space that will satisfy the Bragg condition for scattering photons from this direction into the perpendicular direction. Okay, so schematically, we have this dynamical quantum phase transition shown here. So on one axis, you have the pump intensity, or if you like, the depth of the optical lattice along the y direction. And there are two relevant observables that you can look at. One's the number of photons inside the cavity, and then the other is this order parameter, which tells you about how your atoms arrange in this checkerboard pattern given by cosine ky, cosine kz. So it's the overlap of this potential with the atomic distribution. So for weak pump intensity, we expect that the ground state or the steady state or stable configuration corresponds to just a homogeneous distribution of your BEC. So you don't scatter photons into the cavity because of destructive interference. And the order parameter is 0, right? At some point, at some critical value of the pump intensity, as I've said in the previous slide, it becomes energetically favorable to occupy the cavity mode, and the atoms will self-organize into a density wave checkerboard pattern as depicted here. When they do so, you start scattering photons into the cavity, you get this non-zero number here. So these are the two phases, these are the two competing phases that we have in the atom cavity setup. So we have on one side of the transition, a homogeneous BEC phase, and then the other side, you have the density wave phase. Okay? And note that when you go into the density wave phase, the system will break discrete symmetry, right? The Z2 symmetry in particular, because the atoms will have to spontaneously pick one of the two possible checkerboard configuration, either you localize on the odd sides or on the even sides, right? Okay, so that's all in good. I can see that I'm kind of running out of time, so maybe I would have to hasten my pace a little bit. So there are two regimes in the atom cavity setup. So far, I've only discussed the bad cavity regime. And this is the seminal experiment done by Tillman and Slinger and his group back in Zurich, where they indeed look at this atom cavity setup and they realize this self-organization phase transition. So this is the pump intensity on the x-axis. On the y-axis, you have the pump cavity detuning. And then you can see that at some point you have this critical value for the pump intensity where you start scattering photons into the cavity. And then if you look at the atoms, you see that in the self-organized phase, which is this last column here, you see those Bragg peaks appearing, telling you that the atoms are self-organized or they're organizing this checkerboard pattern. Okay, this is another regime, which is this good cavity regime, where kappa is of the order of the recall frequency. So this means that, theoretically speaking, you can no longer adiabatically eliminate your cavity dynamics. You have to treat them on equal footing. You have to solve them simultaneously, if you like. So another way of looking at it is that in the bad cavity regime, you have an instantaneous infinite range interaction as mediated by your cavity. On the good cavity regime, you have a retarded or a dynamical infinite range interaction. And this will be the main focus of this talk. So in particular, what we did, because we're interested in periodically driven system, we decided to drive or to introduce a periodic modulation in time of your pump field. So it's given by this. So again, epsilon naught is just the pump intensity. F naught here would be the relative strength of the drive, and omega d is the driving frequency, right? And our choice of simulation method is the so-called truncated Wigner approximation, which is a semi-classical method that includes a leading order quantum correction to mean field. And in a nutshell, in terms of implementation, this is how it looks like. So the first step would be to sample the Wigner quasi-probability distribution of the given state that you're interested in. So for example, if it's a coherent state, then it's a Gaussian distribution. And you take a bunch of initial states and then you propagate them in time according to the corresponding Langevin equation describing your atom cavity setup. I can see that there's a question.
Sorry, Jayson, once again.
No worries.
Just wondering, in the earlier one, you mentioned that you do, and so it's within the adiabatic limit, right? And
right.
Now you want to look at the actual time dependencies, but what happens in the infinite frequency, I mean, extremely fast limit to this problem?
You mean kappa is extremely fast? Yeah.
So the
what
period of the driving,
are we talking about?
So I am talking about the driving frequency being extremely fast because this normally renormalizes the Hamiltonian.
Right.
And so what happens here in that case?
That is the story of the first part of this talk. Yeah. That's a good insight. Yeah.
Okay. So that's the first part, right? So that was the first driving. Mm-hmm.
Right. So I will talk about what will happen to the system if you in the infinite driving frequency limit. So you're right that you basically get an effective Hamiltonian, and let's see what will happen to the phase transition. Right.
Okay.
It's
so
literally the next slide.
About it. All right.
Yes, I will talk about it.
Thank you. Sorry.
Yeah. No worries. It's all good. Right. So as I was saying, so the second step is this is propagation of your initial states according to the mean field Gross-Petevsky, if you like, equation describing your atom cavity system. That at each point in time, whenever you are calculating the expectation value of an observable, you take an ensemble average over the multiple trajectories that you sampled. Okay, and we're interested in two observables, namely the number of photons inside the cavity or the cavity mode occupation given by alpha squared, and the number of atoms in the lowest, number of atoms in the lowest momentum mode, which we call the BEC mode, which is this n naught over n being the total number of atoms in the system. Okay, so I mean, this is more or less the kind of main takeaway or summary slide, if you like. So for this type of driving, we obtain the following dynamical phase diagram by looking at the long time behavior of the system. So again, F naught is the driving strength. Epsilon naught is the DC component, if you like, of your pump. Right, this is the constant part of your pump. And what we see here is a renormalization of the phase boundary. So as you increase F naught, as you increase the modulation strength, you further push to higher values of the pump intensity, the BEC density wave phase transition. So you stabilize the BEC phase, right? So kind of similar to this light-induced superconductivity or this Kapitsa stabilization mechanism that we talked about earlier. Okay, so that is for this part of the phase diagram for weak driving. But for intermediate driving, you end up with this discrete time crystal phase, or like I mean, in essence, it's a period doubling response, okay? So in nonlinear physics language. So first, let's look at what happens in this part of your phase diagram for weak driving, right? So as Juzar already mentioned, you can effectively look at the infinite frequency or the high frequency limit of the system by obtaining an effective Hamiltonian according to this Floquet-Magnus expansion. So the idea is that you have a time-dependent Hamiltonian, and then you try to obtain a time-independent Hamiltonian with the hopes of getting some useful physical insight about the effects of your driving, right? So if you do this for the atom cavity setup that we have, so we get the following. So again, just to remind everyone, this is the form of driving that we have. Delta E is just the kind of the absolute modulation strength. And we have a bunch of operators that are introduced here. They're not so important. Perhaps the most important thing here is just the order parameter operator, which, as I already mentioned, it just calculates the overlap between your pump cavity checkerboard lattice and the atomic distribution, right? So this theta is 0 if you're in the BEC phase, and it is non-zero if you're in the density wave checkerboard phase. Another thing that you have to keep in mind are the new constants appearing here, namely the eta, D, and F. Their actual numbers are not so important. What you have to keep in mind is that they're all positive. Okay, so they give positive energy contribution to the system. Okay, so let's maybe unpack this Hamiltonian a bit more. So the first line here is just the undriven part of your Hamiltonian, right? And originally, you actually have this atom cavity coupling included there. But because of driving, you get this new term here, which is proportional to delta E over omega D squared, because, I mean, this is what you get from this Floquet-Magnus expansion. It's an inverse frequency expansion in powers of 1 over omega squared. And what you have is a renormalization of the atom cavity coupling. So what basically happens is that you're effectively reducing the atom cavity coupling by introducing this periodic driving. And then, in addition to that, you also get these new terms, okay? And they serve as energy penalties for occupying the cavity mode or if your atoms self-organize, right? Because, again, they're all positive energy contribution. And if they're non-zero, then they will increase the energy of the system. So in a nutshell, so the first line here is the original kind of energetics of the system. But because of periodic driving, you are penalizing, so to say, the formation of this self-organized checkerboard pattern in the scattering of photons into the cavity. And maybe just a side remark, maybe some of you working in the field of quantum optics may have already recognized that this term here is reminiscent of the typically neglected diamagnetic term in light-matter interaction. Usually originates from the gauge invariant. So it's this A dagger plus A squared. So in quantum optics, if you're familiar with the Deca model, you know that it has a superradiant phase transition, and this term here, if you include it in your Deca model, it will actually suppress the formation of this superradiant phase precisely because of this reason, because occupying the cavity mode will it's just energetically not so favorable, right? Okay, so now if we take this effective time-independent Hamiltonian and run our simulation, just solve the corresponding equation of motion, we get this boundary here given by the purple curve. So again, we identified the density wave phase by having non-zero cavity photons, and we identified the BEC phase as having zero cavity photons. Okay, so that's how we kind of distinguish the two phases. Right. So I'm kind of running out of time, but okay.
You still have time. There were several questions, so.
Okay.
15 minutes let me know. Easily. 15 minutes is still good.
Sounds good. 15 minutes. I hope that should be enough. Right, so if we look at a single mean field trajectory, so now I'm going to be simulating the full time-dependent model, okay? So let's forget about the effective time-independent Hamiltonian for now. I mean, it's useful because we're able to get an interesting physical insight on like kind of like an approximation on what would be the effects of periodic driving in the system, right? So now I'm going to be solving the actual full time-dependent problem using this truncated Wigner approximation. And this is a typical single mean field trajectory that we get. So on the top left panel, you have the momentum distribution. On the top right panel is the single particle density or the atomic distribution. It's a cut along the pump direction. And more importantly, it's a deviation from equilibrium position, okay? So that's why it's 0 initially. On the middle panel, you have the cavity mode occupation, meaning the number of photons inside the cavity. And then in the bottom panel, you have the main control knob that we are changing, which is the pump strength or the pump intensity. And what I'm going to be showing is a result of the simulation for the following protocol. So we're going to linearly increase the pump strength from 0 to 5 milliseconds until it reaches the desired pump intensity. And then from 5 to 10 milliseconds, we're going to keep it constant, allow the system to relax the corresponding steady state. And then from 10 milliseconds onwards, we're going to periodically drive the pump intensity. Okay, so what's happening is, so we are increasing the pump intensity. You get this finite depth, non-zero depth of the optical potential along the y direction, and you start to see this density modulation. So that's not so surprising, right? And if you take the Fourier transform of this, you get the momentum distribution. You start occupying those momentum peaks corresponding to this density modulation. So you're still in the BEC phase, as evident from the fact that you still don't scatter photons into the cavity. So we'll continue with that. You can see that you're getting more atoms in the 2h/k momentum modes. That 5 milliseconds, we keep it constant, and then the system, it turns out that the final pump intensity that we have chosen is already beyond the critical value required for the density wave formation. So that is why after some time delay, and this can be traced back to the fact that kappa is of the order of the recall frequency now, so it's no longer instantaneous. So there's this time delay here. After some time delay, your atoms realize that, okay, it's energetically favorable for us to start scattering photons into the cavity. So we're going to self-organize into a density wave phase. So here they choose the odd sites when they self-organize, and if you look at the momentum distribution, you occupy those characteristic Bragg peaks describing the checkerboard formation. And more importantly, if you look at the cavity mode occupation, you get a non-zero value. So we're keeping it constant, allow the system to relax to a steady state. And then 10 milliseconds, we switch on the drive. And you see that you suppress the scattering of photons into the cavity, and then you recover atoms back to the lowest momentum mode. Okay, so we play this game for different values of epsilon and f naught, and we obtain this dynamical phase diagram. So on the top panel, you have the number of photons inside the cavity, and the bottom panel, you have the BEC mode occupation. So the dashed curve corresponds to the boundary that we obtain from the full simulation of the time-dependent model. And then the solid curve, the purple curve, corresponds to the effective time-independent Hamiltonian that I showed you earlier. And there's a good agreement between the two of them, which kind of suggests that you have this physical picture that we learned from doing this Floquet-Magnus expansion exercise that periodic driving, in this case, effectively reduced the atom cavity coupling, and that you introduce new terms which penalize the self-organization and the occupation of the cavity mode. And as I've said before, we were really fortunate to be working in close collaboration with experimentalists. And so when we told them this proposal, this hypothesis, prediction that we had, they went back to the lab and they tested this, and indeed they were able to observe this phenomenon of dynamical control of the phase. So M here is just a modulation strength. So increasing modulation strength, you suppress more photons into the cavity. And then if you look at the time of flight image, you see that you kind of destroy those checkerboard configuration, right? Okay, so that's the first part of this phase diagram that I showed you earlier. It's this region here for weak driving. So now let's look at the region for intermediate driving. And maybe just to kind of spoil the end of the movie, this discrete time crystal can be understood in the language of nonlinear physics as a period doubling response because of parametric resonance. And to understand this, what you do is you go back to the atom cavity Hamiltonian, and it turns out that you can actually map it into the decay Hamiltonian or into the decay model. And you do this by essentially expanding in the momentum basis, and then only considering the 5 lowest momentum modes. So recall that this is a typical time of flight image or momentum distribution in the checkerboard phase, right? So if you only consider these 5 lowest momentum modes here, then you can define a collective atomic raising and lowering operator given by this, and the population imbalance operator. Now, if you plug this back into your atom cavity Hamiltonian with this approximation, this is low momentum approximation, if you like, you get this decay-like Hamiltonian. So it's not quite the decay model. So if you only consider the first line, then you recover the actual decay model, but you have these additional terms here. So if you just simply forget about them, you just drop them and just consider the first line, then you can think of so what this means is that the self-organization transition can be thought of as an emulation, if you like, of the superradiant phase transition in the decay model. They're kind of approximately the same type of phase transition. Okay, so it turns out that the photonic frequency and the atomic frequency here can be related back to the original parameters that we have in the atom cavity setup. But we're not yet done. We want to map the system into a parametric oscillator Hamiltonian. So the next step would be to apply a Holstein-Primakov representation. So if you do that, you end up with this Hamiltonian in the thermodynamic limit. And at this level, at some point, I mean, at this level, some of you may already realize that this is nothing but a coupled oscillator problem, right? I mean, you have this position operator here, and then you have another position operator. So in fact, if you apply the momentum representation, or if you write the momentum operator and position operator in terms of ladder operators, you get this Hamiltonian, which is, again, this is just a quantized version of a coupled oscillator Hamiltonian. You have this coupling term here, x1, x2, and you have this thing. And you can diagonalize it by going into the normal coordinates, right? You decouple the oscillator by means of a normal mode transformation, and you get this decoupled equation. And if you only look at the oscillator with the lower frequency, you will immediately see that you can recast it in such a way that it will look like a driven harmonic oscillator or a parametric oscillator, where the frequency is modulated in time. So one interesting property of a parametric oscillator is this period doubling. If you happen to drive the if you happen to choose a driving frequency that is twice the natural frequency of your oscillator. Okay, so that's a nice little exercise that we did. So what we learned from this exercise is, one, you can in some approximation, you can look at the atom cavity system as a coupled oscillator problem. And by periodically driving the pump, what you're essentially doing is you are you're basically realizing a parametric oscillator system. And then the other thing that we learned is that you can maybe approximate the natural frequency that we have to match in order to get a period doubling response, right? So if you plug in, yes, please.
Question. To really get a period doubling bifurcation, you need, as you said by yourself, a nonlinear system. But you just on the previous slide showed us a linear problem. So that has instabilities, but doesn't have period doubling.
Yes, exactly.
So where is that hitting?
Exactly. You're well, you're right, because that's a good observation. So this is only period doubling in the specific atom cavity system. If you just don't consider this atom cavity system just a decay model, it's an instability, right? It's not a period doubling response, right? But because in our system, you have those additional terms that we neglected, they provide this non-linearity that essentially stabilizes the period doubling response.
But you do not write these terms explicitly down, is it?
Here, no. Here, I'm just using the parametric oscillator picture to argue that there's an instability. Yeah.
Okay.
So, yeah. Okay. Right. So that brings me to this phase diagram for the full periodically driven atom cavity system. Right. So this is a function of the driving frequency and the driving strength. Okay. And you get this. Some of you may be familiar with this Arnold tongue or this resonance tongue that you see here, right? It is centered nicely around this prediction of the instability, which is around 2 kilohertz, okay? And here I am, as Sergey correctly pointed out, I am not discriminating between chaos and stable period doubling, okay? I will do this later. But for now, we know that there's an instability. Okay, so now if you look at the stable period doubling response in the full atom cavity system, this is what it looks like. So this is a cavity mode occupation, yeah. And if you look closely, so it's quite stable, it's quite long-lived. What essentially happens in your system is that you get these pulses of light appearing. And if you take the Fourier transform of this, it is oscillating at a driving frequency. But if you look at the order parameter describing the spatial configuration of your atoms, you get this periodic switching between odd and even checkerboard at every driving cycle. So that means you need 2 driving cycles, which is period doubling, in order to go back to the initial configuration. So in this sense, you can think of it as a space-time crystal where you break Z2 symmetry both in space and time. Yeah. Okay, so I mean, maybe just to drive home the point that you have period doubling. So here I'm showing the single particle density on the top panel in the long time regime of the system. And what you're seeing here is, okay, after 1 driving cycle, you go from odd to even checkerboard. And then after another driving cycle, you go back to the odd checkerboard, right? Okay. And then they tested this again in the experiment done in Andreas Amerik's group, and then they have this data here. So the blue curve corresponds to the relative phase between the cavity and the pump. This tells you whether you are in the odd or even checkerboard. Okay. And the red curve corresponds to the number of photons inside the cavity. So you get this pulsating behavior in the cavity photons, and you get the period doubling response. You see the period doubling response in the relative phase. Okay, so we can kind of, we decided to look at this in the context of time crystal, and one of the defining features of a time crystal is the robustness against perturbation. So similar to how a solid state crystal, if you just apply a bit of pressure to it, it still remains intact. It has this certain rigidity to it. One would expect for a time crystal to also show similar rigidity. So here what we're doing is we are introducing artificial noise on top of the driving. So we're perturbing the drive a bit, and we're looking at the amplitude of the subharmonic peak in the power spectrum. So you take the power spectrum of your blue curve, right? And then you look at the subharmonic frequency and look at the amplitude of the peak there. And we plot this for different values of the noise strength, and we see that for not so large perturbation in time, you still get kind of like an island where you see nice period doubling. Okay, so maybe just last 2-3 slides. It's important to note that there's this qualitative difference from our theoretical simulations and what they saw in the experiment. Okay, so essentially in our theoretical simulation, we can obtain long-lived period doubling, meaning within the time scale of our simulation, which is around 1,000 Floquet cycles or driving period, we don't see any sign of decay whatsoever. On the other hand, in the experiments, as you have seen in a couple of slides back, you only see the period doubling response within some short time scale, right? So it decays, and it could be explained by the Farlow-Wing differences or factors. In our theoretical simulations, we neglect the short range interaction. We also don't have any atom losses because of driving, and also we only have the standing wave along the pump direction, right? On the other hand, in the experiment, the atoms are interacting. They have collisional interaction. You also have atom losses from driving, and on top of that, you also have a harmonic trap because they have to trap the system. So it introduces an inhomogeneity in the system. So we kind of we look into this a bit more in detail, and it turns out that if you include a short range interaction in your simulation, you basically break the mean field solvability of the decay model, and this can lead to a destabilization of the period doubling dynamics. So we show it here in the red curve when we switch on contact interaction. That maybe it's better if you look at the unequal time correlation for your photon. So for no contact interaction and no atom losses, you get this period doubling response, is stable, long-lived period doubling response. For weak contact interaction, it still remains there, at least within this time scale, right? But for sufficiently strong collisional interaction, you only get a metastable period doubling response before you eventually get something irregular, as you can see here in the red curve. So the red curve corresponds to the case when you have strong contact interaction. And if you include undesired atom losses on top of it, you get this envelope around, this is kind of exponential decay envelope around your signal, which is reminiscent of what they have seen in the experiment. So in a nutshell, we're able to kind of pin down the difference to the presence of contact interaction and also undesired atom losses. So to summarize, so we look at this periodically driven dissipative system, this atom cavity platform, and we were able to show both theoretically and experimentally that by increasing the driving strength, you can either renormalize the phase boundary similar to light-induced superconductivity, or you can push the system to enter a new dynamical non-equilibrium order, just like a time crystal phase. So again, these are just collaborators working with, and thank you everyone for your attention.
Thank you, Jayson, for this wonderful talk. Let's thank our speaker.
Thank you.
So we have time for questions. Please raise your hands.
Let me maybe start, since I anyway cannot raise my hand. So yeah, thanks, Jayson. Very nice talk. I question about this this heating, which you mentioned at the beginning, which should destroy, for instance, also this time crystal. Is that the reason which now the you mentioned at the end for the
yes, exactly.
So it's simply heating.
It is. It is driving induced heating.
And what is this heating doing? Is it just evaporating your atomic BEC, or is it doing something else within this BEC?
What basically happens is that you can imagine you have this optical lattice potential along the pump direction, right? So what essentially happens is that because of the driving, you start occupying higher bands. And when they do so, you can no longer trap them. So they're energetically larger than the depth of your harmonic oscillator potential, then they just escape.
So you basically just evaporate your atoms out of
right. Yes, exactly. So it turns out that even though there's dissipation in the system, the dissipation rate at least that we have, or at least in the experimental setup, it's not yet cold enough, if you like, in order to completely suppress all the driving induced heating that you have.
Mm-hmm.
Any further questions?
Yeah, let me ask maybe then another question, more philosophical one. So the way you explain this this time crystal is the way I would understand it very easily, which is period doubling in a non-linear dynamical system.
Right.
Conservative or dissipative doesn't really matter.
Exactly.
What about, but the whole hype was and is, I guess, a lot about also, is because of the system, the considered system to be quantum.
Quantum, no. It doesn't have to be quantum, it turns out.
No, I'm saying that the hype about time crystals is because these systems are quantum. And that's I thought always that this is part of the reason why this was such an exciting recent, or is such a recent and exciting topic a lot of people focus on.
Mm-hmm.
So what is your understanding here? Is that that if you because I thought I did understand that yes, in principle you can have new phases due to driving, if you wish, a time crystal or something like that as well, simply by driving a quantum by a system, and maybe adding a few restrictions or taking care of a few other things overheating, and the such. And then you can find these new phases, which means you will have new phases or transitions in a quantum system. So what is period doubling in a purely quantum system then?
What is period doubling? It's still kind of like I would say even within the community there is still kind of a struggle on how to classify a time crystal. What is an interesting time crystal and what is a not so interesting time crystal, right? I mean, it's an ongoing kind of discussion. I don't think anyone has agreed on like a proper definition of a time crystal. But what I can tell you is one of the things that maybe everyone in the field has kind of agreed on is the importance of interaction. Okay, so it is a transition that has to be, in order to call it a phase transition, at least a phase of matter, if you like, it has to be driven by interaction. Okay, so that is the hype, I think, behind the time crystal, that you have this many body interacting system that exhibits a subharmonic response, irrespective of whether it is classical or quantum. It has to be driven by interaction. That is the baseline definition, I would say. I'm not sure if I answered your question, but I think it did. I don't know. I answered a part of it, I hope.
No, that's nice. Thank you.
Yeah.
So more questions from the audience, please. Here we go. Alexei, please unmute yourself.
Yeah, but my question is actually generic. I'm curious how much of a freedom. So, I mean, you started by explaining how a long-range interaction arises when you couple your system of atoms to the optical cavity, right?
Mm-hmm.
So, how much freedom do you have in that coupling? That is, do you couple all? I mean, can you couple part of the atomic system to the cavity, or you necessarily couple the whole of it? So, can you design this long-range interaction?
Question.
How it couples to?
Very nice question. That is why I included this slide here. So, so this is the experimental setup that they have. Okay, so the one on the left. So the yellow thingy that you see there, that is the BEC. At least if you compare it with the waist of your cavity field. Okay, so you can see that it is quite small. It is actually an order of magnitude smaller than the waist of your Gaussian kind of field here.
Yep.
So that means, for all intents and purposes, what the atoms see is a flat interaction, because technically this is a Gaussian TEM mode, right? So it should have some kind of Gaussian profile around it. But what the atoms see is just the peak, kind of like the peak of that Gaussian distribution, right? And there's an experiment done in Ben Lev's group in Stanford where they basically were able to realize a long range but but you see there's a non-trivial dependence in space of the interaction. So you can do it. So you can engineer a system or a setting where the atoms will see the curvature, so to say, of your TEM modes. So,
okay.
But it's an interesting direction because it allows for the possibility of multi-mode cavity, multi-mode cavity physics, because everything that I have discussed here is single mode cavity physics. But it will be interesting, of course, if you have a long range, spatially dependent interaction. I think that's interesting future direction.
Okay, yeah, and another question is related. So you mentioned the checkerboard pattern. Can you generate other patterns? I guess this was just, or I mean, is there a particular reason to choose the checkerboard, or you can have other patterns?
I mean, if you just within the context of this self-organization phase transition, you have no choice but the density wave phase, because that's the only spatial configuration that will allow you to scatter photons into the cavity, right? But what we also did, and I didn't really, I didn't have the time to talk about it in this session, is that you can drive the you can drive resonantly with respect to other momentum excitation, right? Not just around this ±1 h/k momentum modes, but also other momentum modes. If you drive resonantly with those excitation, you can actually realize other higher order density wave phase. So that you can do.
What do you mean by higher order? I mean other patterns or?
Other patterns, yeah, other patterns basically. We call it higher order because you're occupying higher order momentum modes. But yes, it's other density wave patterns.
Okay, yeah, thank you.
Okay, in case there are no further questions, I suggest we thank Jayson again for this wonderful talk and his clarifications. So,
thank you, everyone.
And with this, we conclude.